Exercise 4.4, question number 7. 1 by 1 into 2 into 3 plus 1 by 2 into 3 into 4 plus 1 by 3 into 4 into 5 and so on up to 1 by n into n plus 1 into n plus 2 equals to n into n plus 3 by 4 into n plus 1 into n plus 2. No condition is given. It is for all natural numbers. Given statement we have taken as p of n. To prove that p of 1 is true, consider the first term 1 by 1 into 2 into 3, which is 1 by 6. RHS, wherever n is coming, put 1. We get again 1 by 6. So LHS equals to RHS tells that p of 1 is true. Assume p of k is true. Copy the given statement replacing n as k. This is true. I want to prove that p of k plus 1 is true. For p of k plus 1, copy k statement as it is for the LHS. Write the next term. How to write the next term? Plus 1 by, wherever k is coming, put k plus 1. K becomes k plus 1. K becomes k plus 1. Then there is 1. K becomes k plus 1 and then there is 2. Simplify this answer. First k terms, I can substitute the formula k plus 3 by 4 into k plus 1 into k plus 2 plus the last term 1 by k plus 1, k plus 2, k plus 3. What is the LCM? 4 is there, k plus 1 common, k plus 2 common, here k plus 3 extra. Cross multiply. Already there is k plus 3. Now 4 is here, k plus 1, k plus 2. Extra term I must cross multiply into k plus 3 plus. Here k plus 1, k plus 2, k plus 3 is there. Extra term 4 you cross multiply. Simplify the answer by taking LCM. We get denominator 4, k plus 1, k plus 2, k plus 3. The numerator we shall multiply. K into k plus 3, k plus 3 the whole square is k square, 6k plus 9 plus 4, which can be written as multiplying by k throughout, k into k square, k cube, 6k square plus 9k plus 4 divided by denominator 4, k plus 1, k plus 2, k plus 3. What is the RHS? So wherever n is coming, put k plus 1. RHS equals to, in the place of n, k plus 1, in the place of n, k plus 1 plus 3 divided by 4, k plus 1 plus 1, k plus 1 plus 2. This simplifies as k plus 1, k plus 4 by 4 into k plus 2, k plus 3. Just compare LHS answer and RHS answer. Here we get k cube term, whereas here I get only k plus 1 and k plus 4. Denominator 4, k plus 2, k plus 3 alone is there. K plus 1 is missing. So try to factorize the LHS. To factorize the LHS numerator, since we don't have it there in the RHS, the question is k cube 6k square plus 9k plus 4. Alternative terms, here no number tells me 1. 1 plus 9, 10. 6 plus 4, 10. Whenever alternative terms, the total is same. 1 plus 9, 10. 6 plus 4, 10. So whenever you have like that, we will say minus 1 is a root of it. And if I know minus 1 is a root, let us do it by the division method. 1, 6, 9, 4. Remember, minus 1 is a root. So we put 0, 1, minus 1, 5, minus 5. we get 4, minus 4 and we get 0. So what is the factor that we get? Here I multiply by x square. This is x and this is constant. So what factor that I get? 1 into x square plus 5 into x plus 4. Factorizing this, we get x plus 1 into x plus 4. Just check it. X square, 1x plus 4x, 5x plus 4. In this question, I get k's. So we multiply by k square and k. So we write k square, k. So the factors are, already I put minus 1. So k plus 1. Minus 1 is the root. I write k plus 1. Here also I get k plus 1 into k plus 4. So this factorization part we must be little more thorough with, and we are just recalling from standard 10. So what are the factors? Let us substitute in the LHS. We get k plus 1 into k plus 1 into k plus 4 divided by 4 into k plus 1, k plus 2, k plus 3. 1k plus 1 gets cancelled. We are left with k plus 1, k plus 4. RHS also, the numerator is k plus 1, k plus 4. Denominator 4, k plus 2, k plus 3. RHS also, the denominator 4, k plus 2, k plus 3. So we are able to show LHS equals to RHS. That implies P of k plus 1 is true. And whenever I am able to show P of k plus 1 is true, write the statement. By the principle of mathematical induction, P of n is true for all natural numbers. Exercise 4.4, question number 8. Prove that 1 by 2 into 5 plus 1 by 5 into 8 plus 1 by 8 into 11 and so on plus 1 by 3n minus 1 into 3n plus 2 equals n by 6n plus 4. The given statement we can consider as P of n. To prove that P of 1 is true, take the first term 1 by 2 into 5, that is 1 by 10. RHS, wherever n is coming, put 1. 1 by 6 into 1 plus 4. This is also 1 by 10. LHS equals RHS. Tells me P of 1 is true. Assume P of k is true. Copy the given statement replacing n as k. Now we want to show P of k plus 1 is true. Copy the entire statement. Write one more term. Wherever k is coming, put k plus 1. 3 into k plus 1 minus 1 into 3 into k plus 1 plus 2. Simplify the answer. The first k terms, I can substitute the formula k by 6k plus 4 plus this term as I simplify. It is 3k plus 3 minus 1 into 3k plus 3 plus 2. That is k by 6k plus 4 plus 1 by 3k plus 2 into 3k plus 5. Take 2 out from here, it becomes 3k plus 2 plus 1 by 3k plus 2 into 3k plus 5. As we take the LCM, it is 1 by 2 into 3k plus 2 into 3k plus 5. Just check what I must multiply. 3k plus 2 and 2 are here. Extra term cross multiply. Already 1k is there into 3k plus 5 plus 1 into 3k plus 2, 3k plus 5 is here. What is extra? 2. Cross multiply the 2. So 1 into 2. It is 2 3k plus 2 into 3k plus 5. The numerator k into 3k, 3k square, k into 5, 5k plus 2. Try to factorize the numerator. 3 2s are 6 and we want 5. Naturally, 3 2s are only 3 plus 2, 5, 3 2s are 6. The first term 3k square divide by 3k to write the factors. 3 I cancel. I get k plus 1 into 3k plus 2 divided by the denominator through into 3k plus 2 into 3k plus 5. 3k plus 2 cancels. We are left with k plus 1 by 2 into 3k plus 5. So this is LCM answer. This is LHS answer. Try to find out RHS answer. For finding RHS, wherever n is coming, put k plus 1. K plus 1 by 6 into k plus 1 plus 4. That is k plus 1 by 6k plus 6 plus 4 or k plus 1 by 6k plus 10. Denominator, wherever we have 6k plus 10, I can take 2 as common. So k plus 1 by 2 into 3k plus 5, just compare. RHS is k plus 1 by 2 into 3k plus 5. LHS is also k plus 1 by 2 into 3k plus 5. We are able to show LHS equals to RHS, which implies P of k plus 1 is true, and therefore P of n is true for all natural numbers by the principle of mathematical induction. Exercise 4.4, question number 9, prove that 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial and so on up to n into n factorial equals n plus 1 factorial minus 1. Treat the given question as P of n. To prove that P of 1 is true, LHS, the very first term 1 factorial is 1. RHS, wherever n is coming, put 1. 1 plus 1 factorial minus 1. 2 factorial minus 1. 2 factorial is 1 into 2, that is 2 minus 1, which is 1. LHS equals RHS implies P of 1 is true. Assume P of k is true. Copy the given statement replacing n as k. To prove that P of k plus 1 is true, copy k statement, write the next term. Wherever k is coming, put k plus 1. K factorial is k plus 1 factorial. First k terms, I can use the formula k plus 1 factorial minus 1 plus this term k plus 1 into k plus 1 factorial. Combine these two. What is common? K plus 1 factorial. What is left out? Here it is 1. Here it is k plus 1. This minus 1 write separately. This becomes k plus 1 factorial into k plus 2 minus 1. This is LHS. What is RHS of the problem? Let us do. RHS equals to, wherever n is coming, put k plus 1 factorial minus 1. Or we get k plus 2 factorial minus 1. Check whether LHS and RHS are equal. LHS I get k plus 1 factorial into k plus 2, which is nothing but k plus 2 factorial. Remember, k plus 1 factorial is 1, 2, 3 up to k plus 1. If I multiply by k plus 2, I include one more term k plus 2. So 1 to k plus 2 can be written as k plus 2 factorial minus 1. LHS equals RHS implies P of k plus 1 is true. By the principle of mathematical induction, we prove that P of n is true for all natural numbers. Exercise 4.4, question number 10, show that x power 2n minus y power 2n is divisible by x plus y. So long we were doing problems where we had some LHS left hand side and RHS right hand side. We tried to prove LHS equals RHS and hence the given statement was proved to be true for all natural numbers. But in this method, we do not have LHS or RHS, rather some statement of divisibility. So you need not show LHS equals RHS. Check the statement as such is true. The given statement x power 2n minus y power 2n is divisible by x plus y can be considered as P of n. Check whether P of 1 is true. Wherever n is coming, put 1. So I get x square 2 into 1 2 minus y square 2 into 1 2 equals to this x square minus y square. I can write x plus y. We know the factorization. X plus y into x minus y. Whenever I have into x plus y, I can immediately say it is divisible by x plus y. Whenever I have x plus y into some number, I can immediately say it is divisible by x plus y, and so P of 1 is true. Assume P of k is true. Wherever n is coming, put k is divisible by x plus y. Whenever I say divisible by some term, call it as some multiple of x plus y, that is m into x plus y. So x power 2k minus y power 2k is m into x plus y. Bring y power 2k to the other side to use it in the next step. So y power 2k plus m into x plus y. Call this as number 1, which we can use in the next step. To prove that P of k plus 1 is true, we have to write x power, wherever k is coming, put k plus 1 minus y power 2 into k plus 1. This can be rewritten as x power 2k plus 2 minus y power 2k plus 2. In the power, I have plus symbol, split and write it. So this becomes x power 2k into x power 2 minus y power 2k into y power 2. X power 2k I can substitute from statement 1. X power 2k is y power 2k plus m into x plus y into x square minus y power 2k into y square. Now multiply and write it. Y power 2k into x square. My very first step, y power 2k into x square plus m into x plus y into x square minus y power 2k into y square. Now combine these two terms in which y power 2k is common. If I take it out, I am left with x square minus y square plus the middle term copy as it is, m into x plus y into x square. Y power 2k into, what is a square minus b square formula? X plus y into x minus y plus m into x plus y into x square. In both the terms, x plus y is common if I take it out. Y power 2k into x minus y plus m into x square. All these are numbers. I have some number into x plus y. Whenever I get a number into x plus y, I will immediately say it is divisible by x plus y. And so, P of k plus 1 is true. And therefore, we can declare the statement. P of n is true for all natural numbers by the principle of mathematical induction. For n greater than or equal to 1, by the method of mathematical induction, prove that 1 square plus 2 square plus 3 square and so on up to n square is greater than n cube by 3. Consider the given statement as P of n. Prove that P of 1 is true. LHS first term, that is 1 square. RHS, it is 1 cube by 3, that is 1 by 3. Check whether LHS greater than RHS. 1 greater than 1 by 3 is true. Therefore, I can declare P of 1 is true. Assume P of k is true, just replace n by k. To prove that P of k plus 1 is true, copy this k term as it is. Write the next term. In the place of k, put k plus 1 the whole square. 1 square to k square, we can say greater than k cube by 3. 1 square to k square greater than k cube by 3 plus k plus 1 the whole square. That is equal to k cube by 3 plus k plus 1 the whole square. Let us expand. K square 2k plus 1. Taking LCM, it becomes k cube plus 3k square plus 6k plus 3 divided by 3. Now I want to show n cube by 3. So let me write what is RHS. What is RHS? Wherever n comes, put k plus 1. So k plus 1 the whole cube by 3. So I want to compare RHS and LHS. So LHS must be written in terms of k plus 1 the whole cube. What is k plus 1 the whole cube? Let me write. K plus 1 the whole cube is k cube 3a square b, that is k square, 3ab square, that is 3k plus 1. Using this result for the numerator, I can write k cube 3k square plus 3k. Here I have 6k, but I need only 3k. So put 3k plus I want only 1. What is remaining? 6k is there, but I am writing only 3k. So extra 3k. 3 is there, I am writing 1 only. So extra 2. Check, because I want to write in this model. 6k I write 3k plus 3k. 3 I write 1 plus 2. The whole thing divided by 3. So this I can write k plus 1 the whole cube plus 3k plus 2 divided by 3. LHS answer k plus 1 the whole cube plus something by 3. Whereas RHS answer is only k plus 1 the whole cube by 3. So what will you say? LHS is k plus 1 the whole cube plus some answer. That tells me LHS is more than RHS, or I will say LHS greater than RHS. Therefore, P of k plus 1 is true. Hence, you can write by the principle of mathematical induction, the given statement is true. So, problems of this pattern is little different because we are not equating LHS and RHS, rather we are telling LHS greater than RHS. For P of 1, LHS is greater than RHS. For P of K, we assume the result and we try to prove P of K plus 1 comparing LHS and RHS. I could say LHS is having some terms extra. So this term tells me LHS is more than RHS, and so we can conclude the statement. Exercise 4.4, question number 12. Prove that n cube minus 7n plus 3 is divisible by 3 for all natural numbers. The given statement is divisible by 3. We will assume as P of n. Prove that P of 1 is true. Wherever n is coming, let us put 1. 1 cube minus 7 into 1 plus 3. That is 1 minus 7 plus 3, which is minus 3. Minus 3 is divisible by 3. The word divisible by 3 tells me that particular answer is a multiple of 3. So this is 3 into minus 1. Naturally, it is divisible by 3. So we say P of 1 is true. Assume P of K is true. Wherever n is coming, let us put K. Divisible by 3 tells me I can write K cube minus 7K plus 3 is a multiple of 3, or I can say 3m. This further tells me wherever K cube is coming, put 3m plus 7K minus 3, which we will use in the next step. What is my next step? To prove that P of K plus 1 is true. Wherever K is coming, put K plus 1. Expand it, this would become K cube plus 3K square plus 3K plus 1 minus 7K minus 7 plus 3. My main idea is to bring 3 into that answer. So substitute for K cube from here. This is equal to, instead of K cube, I can put 3m, 7K minus 3. Second term onwards, copy as it is. See, anything gets cancelled. 7K cancels. The remaining terms, let us add together and write. 3m plus 3k square plus 3k. All the numbers together, minus 3 plus 3 also cancels. 1 minus 7, I can write minus 6. Check whether we have written all the terms. 3m, 3k square, 3k, 1 minus 7 is minus 6. In all the terms, 3 is common. If I take 3 as common, m, k square plus k minus 2. Here all are numbers. Some number into 3 tells me it is divisible by 3. Whenever I have a number into 3, I am able to say it is divisible by 3, and therefore P of K plus 1 is true. Hence, we can conclude the statement. P of n is true for all natural numbers. Exercise 4.4, question number 13. Prove that 5 power n plus 1 plus 4 into 6 power n when divided by 20 leaves a remainder 9 for all natural numbers. The given statement we shall call as P of n. To prove that P of 1 is true, 5 power 1 plus 1 plus 4 into 6 power 1. 1 plus 1 is 2. 5 square is 25. 4 6 are 24, which is 49. When we divide 49 by 20, 2 20s are 40, the remainder is 9. So we will say this number leaves a remainder 9 when divided by 20. Therefore, P of 1 is true. Assume P of K is true wherever n comes in the question. Write K. Whenever I say it leaves a remainder 9, what does it mean? 49 is 2 into 20 plus 9. So this answer will be some number into 20. That some number we don't know. So we write 20m plus 9. Where m is some natural number. Here it is 2 into 20, or I can say 20 into 2 plus 9. Instead of that into 2, we put any other multiple, say m. To prove that P of K plus 1 is true, wherever K is coming, let us put K plus 1. This is my question. K plus 1 plus 1 plus 4 into 6 power K plus 1. How to simplify this? 5 power K plus 1 into 5 power 1, because I can write what is 5 power K plus 1 from here. What is 5 power K plus 1? 20m plus 9. This I can bring it to the other side. Minus 4 into 6 power K. So this K plus 1 up to K plus 1 I have some answer. Call it as number 1, which I can use it. So 5 power K plus 1 into 5 power 1 plus 4 into 6 power K plus 1, I can write 6 power K into 6 power 1. This is equal to, instead of 5 power K plus 1, substitute this answer. 20m plus 9 minus 4 into 6 power K, the whole thing into 5 plus 4 into 6 power K into 6 power 1. Further, how to simplify this? I can multiply 5 into 20 m can be written as 100m plus 5 9s are 45 minus 5 4s are 20 into 6 power K plus 4 into 6 is 24 into 6 power K. Combining these two, we can write 100m plus 45. This I can write 4 into 6 power K. Our question is, the term should leave a remainder 9 when divided by 20. So this number 45, we want a remainder 9. So take 9 out and write the remaining. 100m plus 4 into 6 power K plus 45 I write as 36 plus 9. Combine the two terms. I get 100m plus 4 is common. 6 power K plus 9 plus 9. We will say 100m is divisible by 20. Also, 4 is divisible by 4. 6 power K plus 9 is divisible by 5. Any power of 6 plus 9 is a multiple of 5. 6 power 1, 6 plus 9, 15. 6 power 2, 36 plus 9, 45. So we can prove it separately. 6 power K, 6 power any number plus 9 is always divisible by 5. Therefore, the product 4 into 6 power K plus 9 is divisible by 4 5s are 20. So these terms together divisible by 20 plus 9 tells me P of K plus 1 is true. So P of K plus 1, as we started doing, it is divisible by 20 and plus 9 tells me it is also leaving a remainder 9 when divided by 20, and so we can write the statement. Therefore, P of n is true for all natural numbers. Try 14th problem in the same way and check out your answer.